Okay, now that we know the basics of charge, it's time to get into the nitty-gritty of atoms. On Schoology, we've got a periodic table right here. Okay, that's going to have a wealth of information for us for figuring out what matter is made of. You'll never need to memorize the periodic table. It'll always be available to you if you need it. Okay, what you need to know is how to extract information from it. We are going to be looking at an assignment today, atomic and isotopic structure. So what are atoms made of? What does it mean to be an isotope? How do elements fit into that? We're going to be having a separate page for notes here. So clicking on this here. This is not something that needs to be turned in. It's just kind of for your own benefit. I'm going to open it with Cami. Okay. Start with, yeah. Okay. Name. Period. Don't worry about that. Okay, so to recap some stuff about charge, right? Like or same charges, so that would be like positive, oops, or that, a negative. Okay, like or same charges repel each other. And if you have opposite charges, like a positive and a negative near each other, those attract each other. Opposites attract. Right? In the atom, we have charged particles. Okay? And it's part of what makes atoms so exciting and so interesting, what makes matter work the way we know it from our everyday lives. Okay? Protons are positively charged. Okay? They're part of something called the atomic nucleus. That's basically the center of the atom. Okay? So the center of the atom has our positively charged protons. Okay? Now the number of protons is what we call the atomic number. Okay? And that defines an atom's element. Okay? What makes something carbon or gold or helium, okay, is just determined by the number of protons. There are other parts of the atom, but the only thing that determines what element that atom is, what type, basically, of atom it is the number of protons. You can find the atomic number, which is the number of protons, on any element block, like maybe this is carbon right here, okay, either by looking at the top middle or the top left. And I believe on our periodic table on Schoology right now, you have it up in the top middle, but usually it's kind of the biggest number on there. No decimals, just a single number dead on. Again, this is the atomic number, which equals the number of protons. Okay. Now, we also have other charged particles in the atom, like electrons. Electrons are negatively charged. Now, electrons are much lighter and much faster than the protons, and you can kind of imagine it like a little yappy dog in comparison to a proton, which is holding on to it with a tight leash we call electric attraction. It's a charge attraction. So the protons and the electrons attract each other, but the electrons are too light, too fast to be just held tightly into the nucleus. Okay, so instead they're part of what we call the electron cloud. We tend to call it that because if we have some positively charged nucleus here, and we have our little electron zipping around, maybe it goes here, and maybe it goes there, or there, or there, and it just goes around, 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 around. And the attraction will hold it somewhat close to the nucleus, okay, to an extent. And we kind of wind up with this area that the electron can be in around the nucleus, okay? And it kind of winds up being like a cloud of where we're most likely to find the electron. We don't really care about a specific location of the electron. We care more about the zone that it's in. And we'll talk more about that in Unit 3. Okay, so the middle is the atomic nucleus, and outside of that we call the electron cloud. Okay, and again, the electron cloud is outside the atomic nucleus. Okay, now opposites attract. All right, so when they get near each other, they're going to keep getting nearer and nearer. They attract closer and closer to each other. Okay, so if I have a positively charged particle and a negatively charged particle, they feel an electric force that brings them together, that attracts them together. Okay, when they get close enough, like in the range of putting protons and electrons together in an atom, okay, their charges effectively cancel or neutralize. Okay? You can kind of think of this like if I had a proton that had a positive 1 charge and an electron that had a negative 1 charge. When they get close enough together, those charges cancel out to be essentially 0 or neutral. Now, does this mean that the proton and the electron are no longer charged? No, they keep their charge. Otherwise, if they were no longer charged, they wouldn't stick to each other. The atom would fall apart. Okay, so the proton is still positive, the electron is still negative, but from the outside, we don't feel that attraction anymore. It's kind of like they are satisfied. For every positive charge that meets a negative charge, they don't need to attract other things anymore. That force cancels out from the outside. So from the outside of an atom that has the same number of protons and electrons, we don't really feel that pull like we would. So most of the matter we deal with, kind of early on in chemistry especially, is neutrally charged. Okay, atoms that kind of float around on their own just tend to be neutrally charged, which means they must have the same number of protons as electrons. For every positive charge, there has to be a negative charge. Okay? So for now, we can assume that all atoms are going to be neutral. The positive charges are always going to equal the negative charges. We're going to have the same number of protons and electrons in an atom. Since we can find the number of protons just from the periodic table, okay, that's the atomic number, we can also use that to be the number of electrons. Okay, so the atomic number also tends to give us the number of electrons. Okay, especially for now, we can always assume it's going to be equal to the number of protons. Now, not everything in the atom is charged. We have one more particle to talk about that's called a neutron. Okay, so neutrons are neutral. They are uncharged. They're not positive. They're not negative. They are also part of the atomic nucleus. Okay. Now, the fact that they don't have charge can be a little bit confusing because the atom sticks together, as far as we know, because we've got protons and electrons that attract to each other. Well, if we throw in something that has no charge, why would it even stick around? Well, it's kind of mysterious. We have something called the strong force. We needed to have a force that explained why the neutrons held so tightly in the nucleus with the protons. So we need a force that was strong. We call it the strong force. If you want to know more about it, you take a class in particle physics, or go searching online, or you can ask me if you're really curious, and I can try and dig into it a little farther. But for now, all you need to know is the neutrons are held into the nucleus by something called the strong force. So that's just basically our explanation of why they don't just kind of drift away as the nucleus does other stuff with its charged particles. Okay? Now, the neutrons also have kind of a benefit. Since our nucleus is made up of protons and neutrons, if it was just protons, we would have all these positive charges repelling each other. The nucleus would essentially tear itself apart because all these protons are pushing away from each other. They have to repel each other. Okay? So having neutrons in between kind of helps to cushion that. Okay? We tend to have about the same number of neutrons as protons in small atoms, but as we get to bigger and bigger atoms, the number of neutrons climbs more and more and more. So we kind of overpass that ratio. Okay? But the trickiest thing about figuring out what an atom is made of is there isn't really a set specific number of neutrons to make an atom happy. There are guidelines, but they can be all kinds of stuff. So it makes it a little bit tricky. Since neutrons don't have charge, we can't just say, oh, I have to cancel the charge here to make this atom neutral or something like that. I can have a version of carbon that has 6 neutrons, kind of like it's 6 protons, but it could also have 7, or it could have 8, okay? And that atom can still be relatively stable. When we get into nuclear chemistry, kind of later on in this unit, we'll talk about kind of some of the other specifics of this where we can tell why something is not stable from the nucleus. But for now, we'll leave it at that. So if we can have different versions of atoms of an element that have the same number of protons and the same number of electrons, but they have a different number of neutrons, we need a way to kind of define those, to describe them so we can tell them apart from each other. Otherwise, I've got 2 atoms, they're both carbon, they both have 6 protons, okay, and they have 6 electrons to match. But one of them is a little bit heavier. It has an extra neutron here or there. Or one of them is a little bit lighter, okay, and it has one less neutron than something else, or 2. So we need another way to describe this. We call those things isotopes. Isotopes have the same number of protons. So we are dealing with the same element, and I'm actually going to color code this. Number of protons, but a different number of neutrons. Okay? So in order to tell apart one version of an atom from another, that's the same element, okay, what we call an isotope, to tell isotopes apart, we use something called the mass number. Okay? The mass number is the number of protons plus the number of neutrons. Oops. Okay, so isotopes only differ in mass. The only difference is they have a different mass. Okay, they have the same charge. Okay, having more or less neutrons doesn't change the charge. All it changes is how heavy that atom is. Okay, so what's your assignment going to look like? Well, we're going to be using what we know about atoms to kind of figure out how many protons, neutrons, and electrons make something up, as well as how we kind of assign a name to a specific isotope. So we're going to look at some examples down here. And I'm going to change my color coding a little bit. So up there I used red for protons, blue for electrons, and purple for neutrons. Down here I'm going to change it a little bit. I'm going to make red is still my number of protons. Okay. which again is equal to my atomic number. I'm going to make neutrons blue. Okay, so that way when we add the protons and the neutrons together, protons plus neutrons makes the mass number in purple. Red plus blue is purple, kind of helps to bring it together. I'm going to use green to show what type of element we have, okay, which again just depends on how many protons we have, okay? So we're going to look at this just kind of like row by row, like this one across here, and this one, and then this one. So this first one, we've got the element Mg. If you look that up in the periodic table, it's magnesium. It's atomic number 12. So you can just kind of keep counting through until you find the big number 12 on there, and that should be magnesium. This specific version of magnesium has a mass number of 25. Okay? Well, I know that magnesium has 12 protons because that's what makes it magnesium. But how many neutrons does this specific version of magnesium have? Okay? Well, since my mass number is my number of protons plus neutrons, and I've got 25 protons plus neutrons, I can subtract out the 12 protons I know I must have and wind up with the number of neutrons. So 25 minus the 12 protons I have leaves me with 13 neutrons. Okay, all right. Okay. Now, if I want to put a lot of information together about an isotope kind of in the same place, we can use what's called an atomic symbol here, where I tell what element it is by using the little 2-letter code or 1-letter code on the periodic table. In this case, magnesium's is Mg. Right. The atomic number that defines it as magnesium goes in the bottom left. Put the 12 there. Okay, and then my mass number, which kind of helps me tag or identify this specific isotope of magnesium, goes in the top left. Okay, now this is kind of clunky, and you can't really say this in words, like, oh, magnesium 25 in the top left, 12 in the bottom left. So atomic symbols are great for writing out, but not so much for speaking. So if you want to be able to say the name of an isotope, we do it a little bit differently. We have just the name of the element written out, like magnesium. Then we use a dash, and then write our mass number, protons plus neutrons. In this case, 25. So we would call this specific version of magnesium, magnesium 25. So that way we can tell it apart from other versions of magnesium, like magnesium 24 or magnesium 26 or 27. Okay, let's look at another example. In this one we've got the element antimony, which seems to have a symbol SB. It's kind of one of the weird ones. And just looking at this, we can glean some information here. Our atomic number is down here, so antimony must have 51 protons, and you can go check that on the periodic table. Okay, but the atomic symbol puts a lot of information right there for us. Okay, our element again is SB. All right, our mass number is up in the top left. In this case, it's 123. Now, I want to show you why I like the way the atomic symbol is set up, because it is pretty much perfect for figuring out the number of neutrons. If you think of this like a subtraction setup, okay, 123 minus 51 should get us our number of neutrons. Now, I cannot do that in my head, and it is too early for me to try and carry the one and do all that stuff, so I'm going to use a calculator. And you may want to as well, because some of these numbers get pretty big and crazy. Okay, but we should wind up getting 72 neutrons for this isotope of antimony. Okay, now we can get all this information even just from the isotope name alone. It might not give us as much information right off the bat, but we can still figure out quite a bit. So for instance, in this isotope here, bromine 80, I know my element is bromine. I can go look that up on the periodic table and find out that its symbol is Br. Right? The 80 after the dash is my mass number, my number of protons plus neutrons. So I'm going to write that down. Okay? If I go and find bromine, Br, on the periodic table, I can find out how many protons it has. Turns out it has 35 protons. That's its atomic number. Okay? Once I know my number of protons and I have my mass number, I can find my number of neutrons. Okay? If I have 80 protons plus neutrons, and I subtract out the 35 protons I know I must have, the rest of it has to be neutrons. So I should wind up with 45 neutrons here. Okay? So all that's left on this one is to write out that atomic symbol. My element is bromine. Bromine must have 35 protons, or else it is not bromine. And this specific isotope of bromine has a mass number of 80. Okay, so on your assignment, you're going to have something like this down here, where you'll be given an isotope, and you've got to find out the number of protons, neutrons, and electrons for each one. So for instance, this oxygen-16 should have 8 protons. We go and find oxygen on the periodic table. It's got a big old number 8 in the top middle or the top left of its block. Something like that. So that's its number of protons. The number of electrons must match that number of protons. Since I'm using blue for neutrons now, I guess I got to pick a different color for electrons. So I'll do like a light blue for electrons. So whatever my number of protons is going to match my number of electrons. Okay? And my number of neutrons is just however much is left in my mass number. I've got 16 protons plus neutrons. 8 of those are protons. The other 8 must be neutrons. Okay? Now in this case, all of these match, but it doesn't have to be that way. Okay? Be careful. It can be easy to fall into this trap of being like, oh, it's all the same number, 888. Okay? But let's look at this other version of oxygen here. This is still oxygen, so it's still going to have 8 protons and 8 electrons to match. Okay? Where this version of oxygen differs is its mass number. Its number of neutrons is different. It's a little bit heavier, it turns out. If this has a mass number of 18, it's got 18 protons plus neutrons. We subtract out the 8 protons, and we actually have 10 neutrons. Okay? So this is a heavier version of oxygen. It's still oxygen, okay, but it's not the same mass. So we have a different mass number tagged to it, so we can tell it apart. Now, finally, you might have information already about an isotope, but we have to tell what the isotope is. So let's figure that out. So we've got an isotope that has 74 protons, 110 neutrons, and 74 electrons. I can tell what element this is with just the number of protons alone. So I go and look for what has an atomic number of 74, and I wind up with tungsten. Its symbol is W, used to be called wolfram, so it's kind of hard to find. You're looking for like a T something, it's a W instead. Its mass number, it comes after the dash, is just the number of protons plus neutrons. Okay, sometimes people jump to protons plus electrons. We don't want that. We want protons plus neutrons. Okay, so 74 plus 110 gives us 184. And that's what we would call this isotope. We call it tungsten 184. Okay? So your assignment is going to be very similar to this, either figuring out the number of protons, neutrons, and electrons in an isotope, or going the other way and figuring out what we call the isotope with a certain number of protons, neutrons, and electrons.